All right. Hey, everyone. Welcome to Solr 4, the SolrCloud architecture. Start off, who am I? My name is Mark Miller. I work for Lucid Imagination. I'm on the Lucene PMC, and I'm an Apache member. I started playing around with Lucene in 2006. I've been a Lucene committer since 2008, a Solr committer since 2009. And this is probably my third or fourth talk on SolrCloud. The last one I gave was in Barcelona, and it was kind of a, what do we plan on doing over the next few months? This talk is basically, what did we get done? The agenda, I'm going to talk a little bit about what SolrCloud is. I'm going to talk a little bit about how it works. And then I'm going to talk a little bit about how we think we know it works. So first things first, if you don't know what Solr is, I'd be surprised, but it's a popular, really fast open source enterprise search platform written on top of Apache Lucene. And so what is SolrCloud? SolrCloud, I just kind of made something up here, but basically it's a set of functions that makes it easy to scale and offer high availability and all those good things, fault tolerance. So in the past, I've taken a few different approaches to trying to explain SolrCloud, and it seems to have gone over well, but I've never been very happy. So this time I've decided to try something else, and let's take it from the approach of starting a little simulated cluster. So this, if you go to the SolrCloud wiki page now, this is a little diagram that I threw up and leads the Solr the wiki page and kind of gives you an idea of the architecture from a very high level. Basically, you have your Zookeeper ensemble on the left. We have 4 shards there. And then there's some extra stuff you don't need to worry about because I'm going to go through it kind of slowly. So before we start up our cluster, let's just talk a little bit about Zookeeper, since that's a pretty important part of this. Zookeeper is a centralized service for maintaining configuration information, naming, providing distributed synchronization, and providing group services. So this is basically the tool we use to do some of the hard stuff, some of the leader election, some of the cluster coordination, that type of stuff. Why did we choose Zookeeper? We actually looked at a variety of projects over the life of developing SolrCloud. And, we really wanted to make sure you don't want to adopt a project into your project that's not, something that's going to stick around, something that's widely used, something that's going to get bug fixes, that type of thing. Zookeeper has pretty broad adoption. I follow a couple Zookeeper developers on Twitter. They're always tweeting about new companies using Zookeeper, people very happy using Zookeeper. It's fairly simple. There's some tricky parts to it, but overall, for what it does, it prevents a really simple interface. And it's really reliable. Yahoo has done huge testing with it on really large clusters. Netflix uses Zookeeper very heavily. They've actually released a few different projects on top of Zookeeper. I know Grant mentioned that this morning. They have, I think it's called Exhibitor and Curator, that kind of help you manage and have a better interface to Zookeeper according to them. We don't currently use either of those, although we may look at them in the future. So, I think the easiest way to think about Zookeeper is kind of as a distributed file system, although it's not really for large data. Each node, really, they want you to have a maximum of a megabyte at it, so it's more for like metadata. But it basically works like a file system. You can see there's a node called Solr. Under that lives a node called Live Nodes. Under that, there's a couple more nodes. Unlike a file system, though, any node can have data associated with it. So let's say a node has children nodes. In a classical file system, the node with children nodes would kind of be like a folder. In this case, the folder can also have data. But otherwise, it's much like a regular file system. So how do we use Zookeeper? We use Zookeeper as a system of record for the cluster state. So that's where we learn about what nodes are up, what nodes are part of the cluster, what their state is. We also use it to store configuration. In the classical distributed setup for Solr, you've got config files living on every node. And so when you want to change something, you got to change it on every node. It's kind of annoying. So we use Zookeeper to have one central place for the config. And then we also use it for leader election, which we'll get into a little later. So before we start up our little SolrCloud cluster, first thing we're going to do is start up a Zookeeper ensemble. So SolrCloud can actually run Zookeeper for you. you can add a couple extra flags and it'll start it up on certain Solr nodes. To get going and to start playing with things, that's a really simple way to do it. And it can be used in production too. There's really nothing that you know, the performance isn't going to be bad. It's not going to just break down. The main issue is that right now, when you start up a Zookeeper ensemble, it's not that easy to change the number of servers in that ensemble. You have to do this rolling restart thing. And so if you start up a SolrCloud cluster and choose a bunch of nodes to host Zookeeper, those nodes are going to be special, right? So if you add new nodes or you want to take nodes away, you gotta consider the nodes that are Zookeeper. And so it's kind of nice to run Zookeeper separately until the Zookeeper team's working on some stuff to make it a lot easier to add and remove nodes. And once they do that, we'll improve our Zookeeper embedded support. But for the moment, we're going to start up an external cluster. Let's say we're gonna start up 5 servers to run Zookeeper. You want a minimum of 3. Because it uses a system, a quorum system, to make sure that you don't have any split brain or multiple, you know, depending on network partitions. You don't want Zookeeper to think there's multiple Zookeeper setups. So you have to. It does this quorum voting that requires that over half of the nodes can vote. So you need at least 3 nodes so that you can have two act as a quorum. So setting up is pretty easy. You basically got to configure on each Zookeeper node, tell it about the other nodes, give it the URLs. And then it's basically as simple as running zkserver.sh on each server. So we run that on 5 servers. Everything starts up. Now we've got on the left there our Zookeeper node. I've got 5 little blue dots to indicate our 5 servers running Zookeeper. And now we're going to start up the 4 Solr nodes. So before I do that, to just talk a little bit about how you control things. We have one knob at the moment to control how many shards you divide things up to, and that also controls basically how many replicas each shard is going to have. So that parameter that you pass when you start up your Solr node is called num shards. And so in this example, num shards is set to 3. So there are 3 shards. Now when you start up the first server, it's automatically going to be given to shard 1. You start up the next one, it's going to go to shard 2, the next one to shard 3, and then every server you start up after is going to be evenly distributed across those shards. So 4, your 5th one will go under shard 2. And you could start up 100, and they're all just going to become replicas of those 3 shards. We're considering adding other knobs for how you control this stuff, a little more fine-grained in the future, but at the moment, this is kind of the simple, easy knob to control these things. Okay, so now we're going to start up each Solr instance. On the first node, that's what's going to bootstrap our config files into Zookeeper. So it has a little bit extra compared to the other ones. It's got this -d bootstrap _conf equals true. Basically, what that's going to do is when you start up this node, it's going to look in your local Solr conf directory, basically, based on Solr home. And it's going to look at all your cores. And it's going to find all the config files for each core, and it's going to upload them into Zookeeper. And it's going to create a collection set with the name of that core. So basically, you could set all your cores up that you want locally with all the config that you want, and then you run this, and it'll just kind of blast it off into Zookeeper. And then the next time, you don't have to do the bootstrap anymore. You've got all that in there, unless you want to change some config. I'm giving it a num shards of 2 because our little example cluster, I want it to have 2 shards, and we're going to have 4 nodes. And then I just give it the address to Zookeeper. To save space, I just put, you know, zk host 9983. Technically, you're going to want to do a comma-separated list of all the Zookeeper servers so that if one goes down, it knows the list of others to connect to. In the future, we also want to try to make that a little nicer. We just kind of inherit that from Zookeeper at the moment, but it'd be nice if there was a place to discover the other nodes easier. So then server 2, we start another node, server 3, server 4. That's going to give us a 4-node cluster, 2 shards, so each shard has 1 replica. So back to here, we've got our Zookeeper, we've got our 4 nodes. And so, okay, now when you start up each node, here's kind of briefly what happens. First thing that happens is the node will register with Zookeeper. Basically, this means, you know, adding to Zookeeper, how do you contact me? What's the URL to contact me? What's my current state? When it first comes up, the state will usually be recovering, because the first thing it's got to do is make sure, hey, am I up to date? Is everything good? Once it's figured that out, it'll either recover or decide it doesn't need to and update its state to active. So now each node has now registered in Zookeeper. Other smart clients or things that you write or other Solr clients, they can now all go to Zookeeper and figure out, oh, this is a 4-node cluster. It's 2 shards. Here are all the addresses. These are the servers I need to ping. These are the servers that look like they're still up, etc. So one of the things it does, and one of the things we take advantage of, is something called an ephemeral node in Zookeeper. An ephemeral node, when a client creates an ephemeral node in Zookeeper, once that client goes down, that node goes away. So we kind of use that as a way to know, with some lag time, what servers are up, so that we're not constantly trying to hit a server that's no longer even talking to Zookeeper. So moving on. So now our 4-node cluster from the new Solr admin view. If you haven't played around with Solr 4 trunk yet, we have a new admin UI, and it's pretty fantastic compared to the old one. Some guy stepped up and has been working on this for months now, and just pretty much adding anything we possibly request pretty quickly, which has been pretty great. So the new admin looks like this. If you're running in SolrCloud mode by passing those properties, like in this case, when you pass the Zookeeper host to connect to, that indicates to Solr that you're running in SolrCloud mode. You're going to get this cloud tab, and when you click on that, you've got these views of your cluster. So in this case, we've got collection 1, which is 2 shards, and there's 4 nodes. The green there indicates that those nodes are active and healthy. The little filled in dot indicates which one is a leader, which isn't really important to the user, but just for helping debug, that's there. If they were in other states, you would see different colors. If one of them was recovering, I think you would see like yellow or something. If one of them failed recovery and was just going to give up, you would see red. So that's one of the views. That's the graph view. There's also a graph radial view, which gives you things kind of done in a circle. It's all really cool, this little library. And because it's HTML and stuff, it can get really big, and you just have to scroll around to see everything. So another view is the tree view. This basically just gives you the Zookeeper layout. That's what is in Zookeeper right now. At the top, there's a cluster state.json. In there is JSON that describes the cluster, each node, and what state each node is in. So that's what you read to determine kind of the cluster layout. Under collections is just kind of some internal stuff we use to do things like leader election and whatnot. Under configs are named config sets. So you can have a config set, name it whatever you want. Any new collection you start, you can point to one of the config sets. Live nodes is a list of those ephemeral nodes, so that you can say, okay, who is up and communicating with Zookeeper and who's not. Node states is where when a new core starts up, it registers its current state there. And then we have overseer leader election, which again the user doesn't really need to concern himself about. So we've got our 4-node cluster up, we've got Zookeeper up, everything is talking. It really just took those like 5 commands, 1 command on each server, and everything is running. How do things work now? It basically works the same as single node Solr works. We want to index a document. We're just going to pick a node. I've got a curl command here to index this little JSON document. That's, it's nothing, just a bit of text and an ID. So now let's look at what happens when you add it to the cluster. So, it's the wrong text there. Let's add this document to the top right node there, which is the dark ones are leaders, the light ones are replicas. So we're going to add it to this little doc to shard 2 to the replica. So what's going to happen? It goes there. That shard is going to hash it to the I'm sorry. This is yeah, okay, yeah. So this shard is going to hash it, determine where it needs to go. It needs to go to shard 1 based on the hash. I'm just making that up. But so what it's going to do is it's going to forward it to shard 1, right? Now shard 1 is going to version the document. So we add a new version. We're good. And then once it versions the document, it's going to forward it to its replica. So why do we version the document? We basically version the document because, say you have like 3 or 4 replicas, and multiple people are trying to update the same document at one time. And then that document's going to get replicated out to the replicas. You need the same the same update to win on each node, right? You want to be consistent. And so you can kind of do that with timestamps and use NTP to make sure all your clocks are in sync or something, or you know, there's kind of various ways, vector clocks, if you're talking about, you know, kind of eventually consistent system. Basically what we decided, and the main reason we have the leader, is we're going to use versions. So that leader will version the document, it'll forward it out, and now we've got the document on shard1 on both nodes, and we're good to go. You keep adding more documents, things keep happening. So once it goes to the replica, if you already have a higher version for a certain doc, then we just drop that update. We're like, we already have something newer, so drop the old one.
When is the ad successful? When does it respond back to the posting system?
Okay, yeah, so currently, I mean, we want to make this kind of configurable, but currently the ad is not successful until each replica has received the update. So it's going to go to the leader. The leader actually currently indexes it locally, and then in parallel, it sends it to every replica. Once those responses come back, it returns. So I mean, the main reason we do that at the moment is it just seemed like, you know, the best first step. We want to make that configurable, but that gives you monotonic reads. You know, once you've done an update, you know any server you hit to query, it's going to be there, which is a nice default. We do want to eventually make it so you can say return after it's on n replicas. And you can say, you know, once it gets to one other replica, return. And we also want to offer fire and forget, you know, just send it to the cluster and don't even wait for responses. And, you know, if maybe you're dealing with logs or something, that works for you. Okay, so that's kind of the simple thing. We haven't really talked about any failures or any of the hard stuff. Like getting that up and going, you know, doesn't take that much. You know, how did we do it? Did we have to rewrite everything? No, not really. A lot of the existing plugin points were used. Some of the things we added, there's a Zookeeper controller class that basically houses kind of all the Zookeeper code and Zookeeper communication code. It's fairly isolated. It's part of a core container. We had to add a new Solr resource loader called the ZK Solr resource loader. Basically, that just knows how to read config files out of Zookeeper instead of the local file system. That was pretty easy. Yannick added a transaction log for durability and recovery, and also, like, you know, part of our real-time get stuff. We added a distributed update processor, which is a current plugin point that does most of the forwarding work and the versioning work and all of that stuff. So that was just a plugin point we already had. We added a real-time get component, which we kind of use for some of the recovery stuff and which you can use as a feature, which we'll talk about a little later. And we added some recovery code for when things go wrong. And we reused the existing Solr replication. Solr replication has been around for a while. It's pretty hardened. It's been going for a few years. So we figured no need to redo that. Let's just tweak some things so that it works for what we want to do. And then we just had to beef up some other code as we ran into things, but nothing major. So before I talk about failure situations, what are some of the things we get from this? We can have near real time now. Solr 4 has near real time support. Now that we're forwarding things a document at a time, you can set up near real time on each node, and you know, you have a full cluster with near real time. Elasticity, we want to be able to grow and shrink easy. Adding more replicas is really easy. Just start up new nodes. They keep adding. Fault tolerance, we obviously want. Durability, we get optimistic locking using the versions now, which is another key reason that we chose to go with the leader in the versions, is so that we could have optimistic locking per document, which gives you atomic transactions at the document level, which, you know, kind of a NoSQL feature that's kind of nice, as well as the real-time get. The real-time get basically lets you, normally in Lucene and Solr, you can't see a document until a new index searcher is opened. So you may have added the document, but until you have to wait, even with near real time, you know, it's going to be half a second or however often you decide to open it before you can see it. With real-time get, that lets you use a different interface to say, look, I don't care if an index searcher can see it yet or not. Give me the latest of what's there. So you can kind of use it more like a NoSQL type feature too. And then we also use that for certain recovery scenarios. So, I mean, all of that was kind of interesting. It wasn't that hard to do, you know, just kind of getting through the code. The hard parts come when it comes to dealing with failure and high availability and things like that. So there's a couple cases with that. One is like, you know, let's say the replica goes down. All these arrows are just kind of random requests, searches, updates, whatever. when a replica goes down, basically everything just moves. You see all of the requests. When a request comes into one of these nodes, it's got to figure out where to send sub-requests to, right, to gather all the documents or whatever. We built in previously load balancing for that. In the past, you had to set up lots of kind of virtual IPs for all sorts of stuff, because each node needs to hit a virtual IP to make sure it's load balanced across, and then at the top level, you needed a load balancer. So we put in a software load balancer on each node so that those sub-requests are all load balanced. You still have to load balance from the outside because you got to pick a server to talk to, and if that server goes down, you're in trouble. We also have some SolrJ clients written in Java that will do that for you. So if you use SolrJ, then you're good. Otherwise, you probably want to build a load balancer outside of it. So what happens then if a leader goes down in this case? Same thing, you got to redirect all the sub-requests and whatnot, but also you're going to end up with a new leader. So we need, basically this is simulating the nodes. Sorry, let me go back. This is simulating the nodes coming back, all right? So the leader goes down, we got to get a new leader, but say that one then recovers. When that one recovers, it's now going to be a replica, and you're going to have a new leader automatically, which is going to do your versioning, etc. Okay, handling server failures. This is basically all the difficulty in everything we did is basically handling failures. So search failures are fairly easy, and we did this quite a while ago. I mean, load balance. You don't get a response back, try a different server. Zookeeper tells us which shards are up with those ephemeral nodes. So at first pass, you just say, okay, which ones look up? They may not be up because Zookeeper works with this heartbeat system, and it's a little delayed. So that's our kind of first approach. If we try a server and we don't get a response, then we load balance. And so that covers, if it's faster than the heartbeat can detect, we're still going to retry when there's a fail. So the search stuff, it wasn't that hard. The indexing stuff is a little tougher. So there's two kind of main failure types that we got to worry about in this case. One, a non-leader replica goes down. That's not too difficult, right? Basically, the leader's just going to stop forwarding documents to that one. It's going to forward it to the other replicas. Eventually, it's got to come back and recover, but it's not too trouble. The other part is if a leader goes down. That's a little more difficult because the leader is getting documents and forwarding them to multiple replicas. Let's say the leader goes down and it's forwarded the document to 2 replicas, but not a 3rd replica. You're kind of going to be in trouble. You got to sync things up. So that's kind of the more interesting thing to solve. And so basically we have 2 recovery options when a node goes down and then needs to come back up. One of them is a simple sync where we receive missing updates. This reuses some of the real-time get stuff where we just say, talk to the leader or the new leader and say, where are you at? And are we close to you? And if we're off by like 100 updates or whatever, then we just trade updates and get back in sync. In the case where a leader goes down and a new leader needs to come up, we kind of use that same sync, but we do it twice. First, the leader syncs with each replica to make sure it picks up any documents that if a leader went down and it sent some documents or some updates to a couple replicas but not another, then when a new leader is elected, it may have been that one that didn't get the updates. So the first thing it does is it syncs with the other nodes so that it can pull in anything that was missing. And then those nodes sync with the leader now that it has everything, because there may be another node that's missing something. So there's this double sync for when a leader goes down that gets you back into place. The other option is if you're off by more than that many updates. Maybe you recover the server like the next day and it's way behind. In that case, we just do a simple full replicate. And we just add a little bit to that. You can't just replicate from a point in time if there's active indexing happening, right? You're going to miss updates because you've pulled that index. So what we do is we start buffering updates using the transaction log. We do a commit on the leader so that to get our commit point of what we're going to pull. And then we pull it while we're buffering updates. Once we're done pulling it, we apply the buffered updates that came in while we were replicating, and then we're in sync. So little animation of that. If it's a small difference, we sync, which is just sending a few documents from the leader to the replica, and we're in good shape. If it's a big one, we send the index across. So I talked mainly about this. What if a leader goes down? That's kind of the hard part. This is basically what I worried about solving for most of the time, and talked a lot with Yannick about you know, how we want to do this and how it was going to work. We have a solution that works pretty well now, I think, and we want to add some more knobs and options, but it works pretty well. So, okay, so that's my claim now is that gives us complete fault tolerance and reliability and scalability and blah, blah, blah. Easy to say. How do we really know that works, right? And how do we continually know that works? Once we finished it all, we could have gone out and manually tried to set up all these clusters and kill machines while we're trying to index and try to test it as best we can. But then any changes you make or any improvements you make, you got to do all that testing again. And are you really testing every scenario and whatnot? So to make sure it really works, you know, we really needed good tests. And honestly, I spent way more time on tests than any coding I did for this, and trying to debug tests and track down failures and whatnot. Luckily, Lucene and Solr have some of the best tests in the open source world, in my opinion. I mean, at least from what I've seen. And they're constantly getting improved. And in fact, they're pretty good. So one of the things that happened is the guys at Carrot Labs, they actually started a new project called Randomized Testing. You can find it there. It basically extracted out a lot of the really good ideas and code from the Lucene and Solr test framework and turned it into something that others could use easily. It's a really great idea. We have a product that we work on at Lucid, and I started copying out all the test stuff from Lucene immediately when we started working on that because it's such great test stuff. It lets you do all this randomized stuff. It has all these improvements to JUnit where it's making sure you're not doing things wrong and printing out errors or warnings if you are, if certain setup methods aren't getting called that you silently don't get called normally, it'll scream about it. All these great things. So I had copied a bunch of code to do that. It wasn't easy to just get the code. And then when Robert looked at that a little while later, he said, oh, this is crazy. We should just be bundling this up as a package in Lucene and Solr so that we can just take the jar. And so for a while, we moved to that. And then Carrot Labs said, you know what, we want to use this stuff for Carrot too. We're trying to use this stuff. So let's make a new project that anyone can use. And that's what this randomized testing framework is. And it basically just gives you a lot of tools to do some really nice tests, especially random tests, which let you explore a much larger space, tries to make those tests very reproducible, prints out, you know, the seeds that you need to use and different things to make the test reproducible. It's really awesome. I mean, in my opinion, if you're writing JUnit tests and you're not using this, you're crazy because I think it's one of the best things out there for tests. So we wrote a lot of tests on this, you know, your standard tests of let's just do the basics. You know, can we start up multiple servers? Can we index to them? Also, we start up a single node control in all cases. So we start up a mini cluster, we start up a single node, we do things to both, we make sure the control matches the cluster, that type of stuff. Plus just other specific tests. That gives us, you know, a base to work from, basically. But how do we really know that this stuff works, right? I mean, in a distributed environment, so many things can go wrong. There's so many timing issues. Servers can go down left and right, you know, one after another in different ways. Different things can be happening and different interactions can occur that a bunch of specific tests can't really catch it all. You know, so how do we really know that it works? The chaos monkey. So if any of you guys follow Netflix much, which you should, they have an amazing engineering department. They release various documents about how they work and what they do, and I think they're kind of on the leading edge of this type of stuff. And one of the things they do is they have this thing they call the chaos monkey that runs actually on their live system and randomly kills EC2 servers on their production system, which is pretty cool, so that they know at all times servers can die and we're going to keep running. And so I thought, you know, that's a fantastic idea, and we basically need something similar, even though we're not doing it in EC2, because these are just tests that you spin up. So I created some tests called the Chaos Monkey tests. And so what does it do? Basically, it builds random clusters, different numbers of shards, different numbers of replicas, and then it continuously stops some of them, starts some of them, while at the same time running multiple other threads that are adding documents really fast, as well as deleting documents really fast. Those are using this special Solr J client called the Cloud Server client, which knows how to talk to Zookeeper, and also does software load balancing. So while servers are going up and down, as long as I'm using this client, I know that I should never see any failures, no matter what, as long as I don't kill every server for a shard, right? You need a server hosting a shard, otherwise if a document hash is there, it's got nowhere to go unless the server is up. So the one thing that it does is it doesn't kill the last server for a shard. It'll just kill up to that point. It'll start them back up. And there's just this one rule that says, hey, if you're about to kill the last shard, don't do it. And also, it randomly expires connections to Zookeeper. When you lose your connection to Zookeeper, you've kind of lost your connection to the cluster. You know, you're out of date, basically. You've got to recover. When that connection comes back, you've got to do a recovery mode because you may have not gotten some updates. So to test that really well, we just kind of randomly kill connections to Zookeeper from each server. So we run it in two different modes. In one of the modes, it kills leaders, which is kind of the more complicated case, like I said. In another mode, it doesn't kill leaders. This is kind of important because this test is hellish to debug, right? There's a lot of timing involved. You can try to reproduce it, but because it depends on how many system resources you have and this or that, it's not going to be the same, right? Servers are going to die at different times, no matter how hard you try to make it the same. So this test isn't great for like, oh, this specific thing broke and now I know what it is and I got to fix it. This test is more a sanity thing of, hey, if it's always passing, things look good. Otherwise, maybe it's failing 1 out of 10 times. If it's failing 1 out of 10 times, we got to figure out why. And sometimes we can spend a couple days trying to nail that down. Sometimes it's failing 1 out of 100 times. And we're like, oh, we got to figure out why. The reason I in one set kill leaders and the other set don't, at least that gives some information of, oh, the one that doesn't kill leaders is passing all the time, and the one that kills them is failing 1 out of 100. So we can say, oh, this is a leader issue. But debugging these tests was a lot of time. But at the same time, it's the only way that I have any confidence that all of this works. Distributed systems are hard. How am I going to prove that you're not going to lose data? I can just say, I don't think you're going to lose data, and then over time, customers report back, and we're like, yeah, they're not reporting we lose data. I mean, that's not very good. This is running all the time. You can set it up to run and say, run for like 6 hours, and the monkey will jump around, killing things. Over there, it's starting a server that's killing the Zookeeper connection. He's blasting that. And you can say run this for 24 hours. And at the end of the day, it's going to do all of these checks, basically, to make sure when it stops, everything still makes sense. So what it does is, it runs for X amount of time, and then it waits. And it starts looking at states and waits for everything to recover, everything to finish recovering. Once everything stops and everything is in like a known state, then we start checking things. We have a control that we're also indexing to. Does everything match the control? They're the same number of documents. We also look at each shard. When you add them all up, does it add up to the number of documents you find when you do a search? Even though when you're picking off each shard, the number, and manually add them up. Basically, whatever assert I could come up with, and to make sure things appear right and you're not missing anything, that's in there. And give the monkey a banana because he did a good job. So that's basically it. There's kind of a fair amount more to it. I didn't want to dive into everything. It's kind of difficult to get too technical on a lot of topics with a kind of varied audience. If you have any further questions or want to talk about anything in more detail, I'll be around for the rest of the day. Yannick Celia is back there. He'll be around. Sami Siren worked on it with us. He's back there. He'll be around. And there were a few other contributors that worked with it too. It wasn't just us, but I'd say Sami, Yannick, and I did the majority of the work so far. Here are some resources to go find more, to go look for it. It's going to be part of Solr 4. There's a loose plan to have a Solr 4 alpha out in about a month. Hopefully we hit that, and then there'll probably be a beta shortly after that. And then, if all goes well, I would think Solr 4 would be out by the end of the summer, I hope. I won't promise that, but that would be my hope. A lot of people are using it now. A bunch of people are using it in production. It definitely works. There's all the normal caveats of working with Solr trunk. You kind of got to reindex if there's an index format change. Once we launch the alpha, I think the Lucene guys plan on committing to try not to put any index format changes in there, just to make things easier for people so that you'll be able to upgrade, unless there's a critical bug where they need to make a change. So once the alpha comes out, it should be safe to start playing with, and then when 4 finally ships, you should be able to just use your same indexes and whatnot. So some contact info, you can follow me on Twitter, my 2 emails, and I blog sometimes at Lucid. I haven't put up a blog post in a while, but I've got a lot from the last couple of years. And if you want to download this presentation after, I got a bunch of other heavy text slides with some kind of more information that'll be online when we put this up. So, any questions? Micro-sharding. You can do your own micro-sharding kind of by just putting using multiple cores and putting all your shards on one machine. And then later on, you start up a replica on another machine, let it replicate over, kill the first one. And so that's kind of the way to initially scale. We plan very shortly on adding shard splitting so that you can continually split. Because micro-sharding will get you so far, but you still got to decide up front how many shards you're going to break it into, and that's going to limit how far you can eventually expand to. So we want to have index splitting as one of the main things so that you can kind of go forever, as well as probably some more help in making micro-sharding easier. You can do it now, but there's some things we can do to make it easier. And so, I mean, that's the elasticity, the final piece of elasticity, I think. Otherwise, adding replicas is easy. Just start up new ones. Taking them away is easy. It's mainly the resharding stuff that we got to finish. Federation between, so I mean, I guess that we plan to add more support for it. Like, say, if you had a SolrCloud in one data center and then another data center, that type of stuff. I mean, that's generally the main thing that comes up, is that people want to support multiple data centers and kind of have 2 clouds running, but maybe one is really kind of compact and just getting a backstream of updates, so that if you do have to split over, then you can start firing up more machines to expand the cloud on the other one. There's some stuff we plan on adding for that type of stuff, but I don't think there's anything immediate that comes to mind. The querying side and how that works is fully pluggable. So exactly what we'll put in out of the box, I'm not really sure yet, but you can actually plug something in that can read Zookeeper. There's an example one that does it now. That's how the default works. That reads Zookeeper and picks the servers. So yeah, I would imagine you could do a pluggable hash implementation and then plug in how the servers are chosen at search time and do that. My split brain slide. Yeah, so Zookeeper uses Paxos, don't know how to say it, algorithm, which is proven to not allow split brain. And so Zookeeper itself isn't going to be split. And Zookeeper is our system of record. Zookeeper describes the cluster, and it can only describe one cluster because there's only going to be one Zookeeper. And so there's really no way for Solr to think it's separate clusters, because it's got to be able to talk to Zookeeper, and Zookeeper has the master record, basically. If nodes cannot talk to Zookeeper, they're going to stop allowing you to index. They'll still in general allow searching, although they're not going to be usually found because Zookeeper's not going to list them. But indexing will, as soon as it loses the Zookeeper connection, it stops accepting documents. So Solr basically doesn't heavily use Zookeeper at all. Like, we don't constantly ping it or whatever. It's only used for state change. As nodes are coming up, they register, and then Solr never talks to Zookeeper other than through watches, where only if something changes does Solr get notified. So in a steady state, once your cluster is up, we're not dealing with Zookeeper at all, really, unless a failure happens. So you don't really need to worry about performance as much as you might for another application that uses Zookeeper kind of heavily and constantly. We really don't. And the thing with Zookeeper is the more servers you add, the worse the write performance is. So you don't necessarily want, unless you really need it, tons and tons of servers. You just want enough to be confident that if a couple go down, you're not going to be screwed, I guess. All good? Time? All right, thanks a lot.